All right, in this video we're going to be studying units of the SI system and tools for measurement. Some of this is going to be really easy. The homework that we're going to be doing in class, you'll see it up here. Well, that's it. We're going to be doing it in class. If you do not already have a translucent metric ruler that uses centimeters and a translucent protractor, make sure you have one by the next time I see you guys. This lesson is going to be focusing on units, and units are not directly tested on the Regents, but really like a majority of the questions that you're going to have to solve involve units heavily. So we're going to study units independently. We have to know them inside and out, and it's just they're not going to be tested directly. So take a moment, pause the video, and think of any units that you can remember from any science class, chemistry or science, anything. Some examples of units I just thought of were joules. You may have had that in chemistry. Milliliters, meters, and inches. So units maybe are very boring to you, but they're really, really important in physics. We think of a unit as a quantity that allows us to compare two things. So for instance, if I were to ask you how close together two cities were, it wouldn't make a whole lot of sense if you just said 26, but it would make a lot more sense if you said 26 miles or 26 kilometers. Now the SI system, or the System International, which is sort of like the metric system, it gives us some standardized units for scientific measurements. We could use fundamental units to express anything, but there are times, because of the size or the quantity that we're measuring, that we'll use a special kind of unit called a derived unit. Fundamental units are the only ones that are, let's say, true. Derived units are convenient, but they are probably made of smaller units. In order to answer this question, which term is not a fundamental unit, let's skip to the next slide and check out the table. So here we are. Which term is not a fundamental unit? Press pause and use the table that you copied down to figure out the answer. Okay, so you've had time to think about this. I can confirm that the answer is watt. Watt is not a fundamental unit. A watt is what we call a derived unit, which means that it has smaller pieces inside it. It's made of other units. You can think of this like a unit for speed, for instance. We often say that a car is moving at 60 miles per hour. Miles per hour, or the unit for speed, is obviously made of two units, miles and hours, which makes it a derived unit. Mile is a unit for length, so that would be fundamental, and hour is a unit for time, so that would be fundamental. So in short, what I'm saying is miles per hour, a derived unit, is made from two units, both of which are fundamental. So here's my table of fundamental units. This table needs to be memorized. I will ask you to pause the video now and copy down this table in your notes. It's extremely important. But just as a quick run through, we have our fundamental units right here, followed by some derived units, which, as I said, are made of fundamental units. And then we have some units down here at the bottom, which are not even SI. They're not System International. So the fundamental units that I want to point out before we go back to the previous slide are length, which is measured in meters, mass, measured in kilograms, time, measured in seconds, current, measured in amperes, temperature, measured in Kelvin, amount, which is measured in moles, and luminosity, which is measured in candelas. So let's go back to the previous slide and answer that question. So over on the right-hand side, we can see a question that I have written. What does this diagram mean? We have arrows going from some units to other units, but there are some units that have no arrows to them at all. There are units that go towards some. Then so they only go out, and then there are other units that only have things being received. So basically, these arrows represent the way that the units can be combined. For instance, you probably know that meters and seconds can be combined just the same way that miles and hours can be combined. So meters per second is a speed, which means that seconds can be applied to meters to make a new unit, or meters per second. At some points in the year, we're going to have to learn to take SI prefixes and convert those units into a different prefix. Remember, SI units relate to each other by factors of 10, which is really convenient, which is why when we do the notations of these units, they all start with a base of 10, and their exponent varies. This table right here is one that you'll find on your reference table, and it goes through some of the most common prefixes for these units. In order, we've got tera, giga, mega, kilo, deci, centi, milli, micro, nano, and pico. And these are the exponents. Down here for decimeter, centimeter, and millimeter, you can see that the exponents are really similar. They're a factor of 10 apart from each other, but then you do start to skip by a factor of 1,000, like when you go from milli to micro. So when you see 3 different in the exponent, that's a factor of 1,000, or 10 times 10 times 10. Now, there is one thing that may become a little bit confusing at later in the year. It's that symbols for SI units are printed in normal type, whereas you'll get italic type if you're trying to do a quantity. So the difference could be illustrated in, let's say, the capital normal type A for ampere. That's a unit. So whenever we have a unit like there were on the previous slide, it says normal font. But then we have these things called quantities, which will be in italics. Here's an example, M for mass. Mass is not a unit. Mass is it's a quantity. Like it's a number, it's a measure of something. For example, the unit that you would use for mass is kilogram. Now that would be a normal type. But since mass is just a quantity, it's very generic and vague, we're going to use italic type for that. Now when you're doing handwriting and you're handwriting out these things, obviously you can't do italic handwriting or like a normal straightforward capital A for ampere. So you're just going to write it like normal, and there might be some moments of confusion, but we need to have a common vocabulary to talk about this, and we'll get it all sorted out. This slide is probably where you're going to start thinking that physics is quote-unquote hard. It's about dimensional analysis. It's going to be a skill that we will use all year long and we will need to master in order to feel comfortable in physics. It's basically a way to analyze units, which helps us to solve problems. The units on the left-hand side of an equation always have to be the same as the units on the right-hand side of an equation. This is pointed at a really basic concept in math, which is that an equation is an expression of equality. So the units have to be the same on the left and the right, just the same as the numbers have to be the same. Following from that, 2 numbers can only be added or subtracted if they have the same units. That doesn't follow for multiplication and division because we can combine the units with those 2 formulas. You can also use dimensional analysis to check whether an answer is reasonable. So it's a way of checking your work if you need to. So here's an example. If M represents mass in kilograms, there's our unit, which is not in italics, and here's our quantity, which is in italics. And V represents speed in meters per second, and R represents radius in meters. Show that the force F in this formula, which I had to write in, can be expressed in this other unit, kilograms meters per second squared. One way to tackle an equation like this is to look at the F equals mv squared over R, and think about them as quantities and start replacing them with fundamental units that match that quantity. For instance, m is mass and it's measured in kilograms, which you need to know. V is speed, which is measured in meters per second, and r is radius, measured in meters. I'm just going to start filling in the variables that represent those quantities. Okay, so I went ahead and I indicated that mass is in kilograms, speed is in meters per second, and radius is in meters, and I'm going to plug those in now. So just for clarity, I'll start out with my original equation, which is F equals mv squared over r, and the m is going to be kilograms this time. I'm filling in the unit for mass, not the quantity. V is going to be meters per second this time. So meters per second is a compound unit, and if you look up in the original, the V is squared. So that means that this whole compound unit needs to be squared, which is to say not just the m and not just the s, but both the m and the s are both squared. And then on the bottom, we're going to have, instead of radius, we'll have meters. Now at this point, you're going to have to do some algebra. One way to do this is to take a look at the exponent on the meters per second first, and sort of distribute it within the parentheses. So I'll go ahead and do that. All right, and then one interesting thing that happens, if I could please draw your attention to this s right here, is that s is going to drop down into the denominator. So it's going to go from right here all the way to here. That's one of the behaviors that we notice a lot with fractions within a fraction, is that the denominators can be combined. So I'll do that now, over on the left-hand side. Okay, so if you're paying attention, you'll be able to see here's the meters per second squared that used to be over there. It's just that I took the second squared and I moved it down to the denominator. There it is. And the meters that was down here, of course, is still there. And then with some pretty basic algebra, you can see that this meters right here and this meters right here are going to cancel to an extent. Since there's actually two, like a meters times meters, or meters squared here, then what I'm going to do is I'm just going to take out this exponent, which is going to indicate that now I only have 1 meter, and it's gone because it canceled this meter here on the bottom. So what I'm left with is kilogram times meter over second squared. And we have just done the goal of the problem, which is to find kilograms times meters per second squared. So that was pretty good, right? Let's try another one. It says, using dimensional analysis, show that the expression v squared over d, I had to write that in, has the same units as acceleration. So you need to know that the unit for acceleration is meters per second squared. If we haven't done that already, make sure I give you an opportunity to memorize those. But we want to use the expression v squared over d and show that it has the same units as acceleration, because at first glance it probably doesn't. It doesn't look like that at first glance. So we'll see what we can manage. I'm going to go ahead and rewrite the original equation, which is v squared over d. The unit, I'm going to use very similar strategy to the one before. The unit for velocity or speed is meters per second, and the entire quantity is going to be squared, not just one or the other. Then the unit for distance is meters, so I'll plug that in. So as you can see, I've just taken the unit for v and pulled it over, taken the unit for distance and pulled it over as well. So now that we have that, I'm going to go ahead and distribute this square into the parentheses. If you remember from the last question, one of the things you can do when you have a fraction within a larger fraction is that you can take the denominator of the fraction that's in the numerator and you can pull it down. That's going to help us here, so let's do that. Okay, so I just managed that. I took the second squared and I pulled it down into the denominator. I kept the meters that was already there. And now we get to do the really fun part, which is to consider the meters that's in the denominator and the meters that are in the numerator and cancel what we can. So this meter in the denominator, I'm going to cancel that out because it's going to cancel with one of the meters that's in the numerator. So I'll take out the exponent, and what I get is meters per second squared, which if you go back to the question, it just says to use dimensional analysis to show that the expression v squared over d has the same units as acceleration. And we did. It's everything that you see right here that I'm circling. That's the answer to the question. Okay, guys, so for this slide, I'm not going to do any recording for it. What I do need you to answer these questions to the best of your ability on your own. And next time I see you, when we're going over the content of the slide and working on practice problems, I think that we'll open with a discussion of these questions. So you need to have them done, you need to have them finished with work shown, and just have them in your binder under notes. These next few slides are a breeze. They're all about how we measure certain quantities, and this one's about measuring length. So basically, I think I can do this one from the bottom to the top. We have this ruler down here, and the main part of the question is, what's the length of the blue wire, and the blue wire is here. So just keep in mind that we're not starting at 0, we're starting at 1. So if that's the case, then we can just go from 1 up to, that appears to be 6.2. So with just some really quick math, 6.2 minus 1, of course, is 5.2. So there you go. It's 5.2 centimeters long. Now on the question about that one, it looks like our focus is primarily going to be on converting centimeters into meters. This isn't such a hard thing to do, but you do need to have some pretty organized thinking. On your reference table on the very front, it'll give you some guidelines about the exponents that match up with certain prefixes. Centi is 10 to the negative 2. I can tell you meters is a base unit, so it's going to be 10 to the 0 or whatever. Let me show you how I would solve this one. And I think that lots of you will probably have your own methods. So I usually think of doing just like the writing down the given information first. In this case, we weren't given like an exact number of meters to convert it into centimeters, but we can make one up for now just to give you an example. Let's say that we have 4.6 meters, and the goal is to convert it into centimeters. So I know that centi is 10 to the negative 2. One of the things you can do is multiply this by a conversion factor. And since you have meters right here as your original unit, which of course I made up, you'd need to have the unit in meters on the bottom of your fraction. And on the top, you're going to have centimeters because that's the one that you want to end up with. Really, what I'm doing here is I'm just canceling this meter with this meter, because when you multiply the two fractions, this numerator and that denominator will cancel each other. Now, in this area right here, I need to have a couple of numbers that make sense, like how many centimeters versus how many meters. So this is going to be the number that you're going to use. So 10 to the negative 2 is centi, and that means it's a number less than 1, 10 to the negative 2. So that means that you've got 10 to the negative 2 meters in every centimeter. You have less than 1 meter in each centimeter. So I'll say that one more time. 10 to the negative 2 means less than 1. So that means you have less than 1 meter in a centimeter. So what I'm going to write down is that in mathematical form, 1 centimeter is 10 to the negative 2 meters, indicating that you have less than 1 meter in 1 centimeter. But they're really equivalent values. So you just combine these fractions. It's going to be 4.6 times 1, which is 4.6, and then divide it by 10 to the negative 2. We don't need to get a final answer here because I remember I made up the 4.6, but I'll go ahead and write it in for you now if you're checking. So I got 460 centimeters. Measuring mass. Just know that there are a couple different ways to measure it. We use a couple different machines. Here we have an electronic balance. This is a triple beam balance. Usually in physics with Mr. Rand, I bet you'll almost always use that guy. So let's just give you some background information. There is this function on an electronic balance called zeroing, or depending on your science class, maybe it'll be called tare. T-A-R-E. The reason why you do that is because let's say that you have this steel ball right here and you want to measure its mass, but you put, let's say, like a paper cup underneath it just to keep it clean for some reason. What you could do is you could lay the paper cup down here, and you don't want to take the mass of the paper cup, just the steel ball. So you could put the paper cup down, and then you could press the zero function or the tare function, and then it would cancel out like the mass of the paper cup, and then when you put the ball on, only the mass of the steel ball would be measured. But it's really important. Also, like, these scales have a little bit of error sometimes, and you can turn them on and it won't say 0 on the reading scale. It'll say some other number. So if that ever happens, press 0 or tare. So the mass in grams of this steel ball there's nothing fancy here. It's 115.2, and the mass of the block of the wood on the triple beam balance, it's a little bit more confusing. So I'm zooming in a little bit, and what you need to do is you need to combine a few different values. Right here, you have a hundreds, and then this is your tens, it looks like, and this is your ones. So you kind of just combine all those things, and it is important that this needle is at the 0 point or the equilibrium point. That's a cutout from down here, by the way. So I think you just add the pieces up. So it's going to be 200 plus 0 from the tens section. And this is like maybe 8.5, so we'll say 8.5. And that's for the ones. So I'm getting 208.5. Measuring time is also very easy. So we just use a clock or a stopwatch. I'd say here's one area where you might come into some trickiness is the conversion from minutes to hours and so on and so forth, because it's not factors of 10. It's like there's 60 minutes in an hour. So let's go ahead and just write that down just for posterity's sake. There are 60 minutes in an hour, and in seconds in a minute, again, it's also 60, which I don't know if that's confusing or if that's not confusing, but when we use a stopwatch, like to measure something, oftentimes, if we're good enough, we'll measure to the nearest hundredth of a second. So check this value out down here, and we'll talk about what value it's actually saying. So right here, this is where you would expect minutes to occur. This is the seconds. Do know there are 60 seconds in a minute, so we're actually almost 2/3 of the way to 1 minute at this point. But back here, these are the hundredths of a second. These hundredths of a second are based on on factors of 10. Not they don't go up to 60. So the 0.08, it won't change this 7 into an 8 until the 0.08 gets all the way back to all the way to 100 basically. So it'll go to 0.99, and then after 0.99, then that 7 will change to an 8. So the elapsed time shown on the stopwatch is 37 seconds, and I'll just use a fraction here, 8 hundredths of a second. So it's basically what it says, 37.08 seconds. So the unit recorded to the left of the colon, that would be over here, that's going to be minutes. The recorded value between the colon and the decimal, or this number right here, that's going to be, of course, seconds. And the recorded to the right of the decimal value, that's going to be the hundredths of a second. All right. To measure forces in physics, we use these things called spring scales. Spring scales almost always have this appearance. Not a lot of craziness going on here. It is a spring. Basically, it's just a spring with a sleeve around it to protect it, and that's why we call it a spring scale. There's different kinds. We have ones in the lab that are 2.5 newtons. We also have ones in the lab that are 20 newtons. And these are SI values, but there are spring scales, of course, that measure in grams, which is an imperial unit, and I think we have some of those in the lab as well. So let's take a look at this question. What's the force being recorded by the spring scale in the diagram? So it's this diagram right here, and just notice that it's between 4 and 5. It looks right in the middle to me, so I'm just going to go ahead and write 4.5 newtons. My next question involves some more, I guess, complex forces. We have this force here, which is a force of tension on the rope. We have this force on the weight, which is, we could call it weight, or we'll call it the force of gravity. And this force right here, that is repelling the two north ends of those magnets, that's going to be magnetic force or electromagnetic force. And then this force right here is going to be gravitational force as well. So that sort of answers those questions. So how are they all alike? Forces are all either a push or a pull. So I would suggest writing that down. Forces are all pushes or pulls. Now, how are they different? It's sort of the origin of the force. So this is a tension force. This is gravitational. This one's gravitational, and this one is electromagnetic. So not all forces are, exactly the same. They can have different origins, but they will all be pushes or pulls. And in your notes, you should maybe copy this diagram and write down, label the diagram with the type of forces that you see there. On this slide, we're going to discuss protractors as ways for measuring angles. This is the kind of protractor that you're going to want to have. It's small, it's translucent, it has values proceeding from 0 to 180 in both directions, it's actually convenient. It can be confusing, but if you use it correctly, it can be convenient. The first thing we need to do here is to answer the question, what's the measure of angle AOB in the diagram below? So I'll zoom in a bit. And it looks like if we're starting at 0, if we're starting at 0, then we're going from 40 up to 50. That's where this line is headed. And this obviously is going to be 45. So this is 46. and this would have to be 47. And just, I'll keep going just to make sure, but 48, 49, and 50. Yeah, so this one's 47. I'll label that now. It says in my second bit that I need to draw an angle of 25 degrees using the diagram below. So I'm going to pause and I'll draw that in and I'll come back. Alright, so I got my line drawn in to the origin. I'm just going to drag it up until I get to the 25 degree mark, which of course is there. So I would just carefully draw that with my protractor and I would be good to go. Alright, so we have to do some trigonometry in physics. It's not going to be nearly as involved as your actual trigonometry class in high school, but we'll do, some trigonometric functions like sine, cosine, and tangent this year. Keep in mind that these functions are only valid on right triangles, so just like this one in this diagram here, you need to have one angle that's 90 degrees in that triangle before really any of these functions are useful. So what type of triangle is pictured below? That is going to be a right triangle. So notice that side A right here is opposite angle theta. So there's angle theta, and here's side A. We consider that opposite. Side B, which is down there, is actually adjacent to angle theta, meaning it's sort of like right next door. So angle theta is formed partly by side B. And then we have, of course, side C, which is what we're going to call the hypotenuse. It's also adjacent to the angle theta, but the hypotenuse is opposite the angle 90, so that's what makes it the hypotenuse. If you know the length of any two sides of a right triangle, you can find the length of the third side without a lot of trouble just by using the Pythagorean theorem. You've probably been using that since you've taken any algebra. So the Pythagorean theorem, of course, is valid for right triangles only, but you can find, if you know two sides, you can find the third side by using this Pythagorean theorem. And if you know one side and an angle, then you can use any of these functions to figure out really basically anything else about the triangle. So we can put some of that into good use right now. It says that we have a block and it's displaced a vertical distance of 0.75 meters. That's basically the height of this triangle. As it slides down a 1.25 meter long plane, inclines to the horizontal at some angle theta, which we don't actually know yet. It wants you to calculate the horizontal displacement of the block. Displacement is sort of like distance, and we just want to know how far the block goes in this direction. Now, if you know any geometry, you know that however much distance it travels this way as it goes down the plane is equal to the length of side B. So basically side B is going to be the exact same thing as the horizontal distance traveled by the block. And that doesn't count the vertical distance that it travels, just the horizontal. So since I know the length of side A and the length of side B, I'm going to use the Pythagorean theorem to do part A, which is calculating the horizontal displacement. There's the Pythagorean theorem. I'll rearrange it if I need to now. Since I'm ultimately solving for B, I'm going to start to show that in my work now. I'm going to isolate b squared, and then finally I'll get the square out. So right now, b squared is being added to a squared, so I'm going to subtract a from both sides, and in my next iteration, I'm going to get b squared equals c squared minus a squared. So I just sort of moved the a to the other side. Now, I don't really want my answer to be b squared. I want my answer just to be b. So one thing you can do is take the square root of both sides. That's the fair way to do it in an equation. And then you will get, ultimately, b equals the square root of c squared minus a squared. So now I'm going to plug in values. B, I don't know, but I'm looking for it. C squared is 1.25 squared. I'm going to subtract from that a squared, which is 0.75 squared. So I just plugged all those values into my trusty calculator, and I got actually a very even 1, and the unit there is going to be meters. So in the next step, which is part B, we need to calculate the angle that the plane makes with the horizontal. So the angle that the plane, which is here, makes with the horizontal there is going to be theta. So I'm going to use a trigonometric function. And a fun fact is that you could use actually sine, cosine, or tangent here, and the reason for that is because we now know the identity of all three sides. We know side A, side B, and side C, and we could use either sine, cosine, or tangent for these. Since side B is the side that we solved for, it's actually possible that there's a little bit of error in that answer. I can actually tell you that there's no error since it came out to be exactly 1, but let's say that there were a bunch of decimals and you rounded it, then you might want to avoid using side B to stop reintroducing error. And that's why I'm going to choose to avoid side B in the function that I choose. I'm just going to try to use side A and side C. If you go back to your reference table, you'll see that the function that matches that, the one that uses side A and side C only, is the function for sine. So it basically just reads that the sine of theta, which we'll end up solving for, is equal to the ratio of side A to side C. We're going to do the ratio of side A to side C, and then we'll figure out how to get the theta itself away from the function sine. I'll teach you how to do that. So basically, the ratio for A to C is going to be 0.75 over 1.25. So go ahead right now, pause the video, and put that in your calculator and get your decimal response. So I got 0.6, which is not the final answer because we are looking for an angle, and 0.6 doesn't make a lot of sense as an angle. But just keep in mind that 0.6 isn't the answer because 0.6 is actually the sine of theta. It's not theta itself, it's the sine of theta. So what we want to do is remove the sine function by performing an inverse sine function, which is basically just like to divide something by sine rather than multiply it by sine. Depending on your calculator, there are different ways to do it. So you might need to look in your directions. But if you're using a TI-34 scientific calculator, an easy way to do that is to press the second key and pi, which is actually the trig functions. And you can scroll down to option number 4, which is, it says sine to the -1. That means inverse sine. You can press enter, and then you can scroll up using the keypad until you get 0.6, which was your sort of decimal response. Press enter, and it'll pull it down into those parentheses. Close the parentheses off, press enter again, and I'm getting 36.869. I'll just keep a few of those digits for now. How about 36.9? Looks good to me. So I'll write that in. And there is my answer. So in summary, I would like you to pause the video so you can see the questions and go back through your Cornell notes and see if you can find the answers to these very important questions. The 7 fundamental SI units. You do actually need to know which ones are fundamental versus which ones are derived. What does it mean to be a fundamental rather than a derived unit? So we've went over this previously in the video, but fundamental means that it's not made up of other units, whereas derived means it may have a basis in another unit. What do you think is the unit for average velocity? So if you use your reference table, you can find an equation for average velocity, and I'll show you what it is now. So v equals d over t, and d is the quantity distance, but it's actually measured in meters, so I'll plug that in. T is the quantity time, which is actually measured in seconds. So the unit for average velocity is actually meters per second, and that's one way to use your reference table and dimensional analysis to solve the question. So also take a moment, make sure you know which devices measure each of these quantities, and lastly, trigonometry is the study of right triangles. All right, so that concludes the lesson. You should have Cornell notes ready the next time I see you.